Good morning students, welcome to online GDC classes. In today's session, we are going to learn about conductometric titrations. So in titrations, we have seen so many types of the techniques. So in that, one of the type of titration, that is conductometric titration. So if you see the picture related to this conductometry in this slide, that is the auto titrator, which is going to be used for conducting the titrations. Okay, so in this conductometric titrations, so many models have already in progress. Okay, that means auto titrator is also available, and manually also you can perform the titration. Okay, and in this you can directly get the readings, and if you use auto titrator, then by using some softwares you can get the titration curve also there. Okay, so directly titration after titration, so you will get the endpoint and titration curves in the software itself. So this is a manual conductometer actually what we have used, right? So this is just an example. Let us first have the glimpse on introduction of what is conductometry. Okay, so conductometry analysis is based on the measurement of electrical conductivity of the solution. So electrical conductivity of the solution, due to the why this electrical conductivity is going to happen, that is due to the mobility of the ions. Okay, so this mobility of the ions, cations or anions, is going to take place towards the respective electrodes. So whenever a cathode and anode is present, then mobility of the ions is going to take place. So due to the mobility of the cations and anions towards the opposite sides, it is going to give you the conductivity, electrical conductivity. So that electrical conductivity we are going to measure it by a instrument that is called conductivity meter. Okay, so the electrical conductivity is entirely due to the movement of ions, mobility, right? So the ability of any ion to transport the charge depends on the mobility of the ion. So the mobility of an ion is affected by factors such as number of ions, charge of ions, size of ions, and temperature of the experiment where we are going to conduct this. So these are the factors which is going to affect the titrometry, conductometric analysis. So if you see the principle involved in conductometric titrations, that is the main principle involved in this method, that the movement of the ions, so whatever the mobility of the ions we are talking about, that creates the electrical conductivity. The mobility is going to create the electrical conductivity. So the movement of the ions wherever towards anode, towards cathode. Okay, so the movement of the ions is mainly depend on the concentration of the ions. So how much amount of the concentration is there. So the concentrations, if you let us examples, if you are going to say A, B is a solution of the strong electrolyte. Okay, so these two are the present in strong electrolyte solution, and C, D the solution of the reagent. If it is a reagent solution, and in that A, B solution is the electrolyte solutions. Okay, so then what happens? The ionic concentration of the A plus, because A and B are the electrolytes, they can be divided into cations and anions. So the ionic concentration of the A plus ions is determined by reacting the electrolyte solution with the reagent solution, that is with CD, right? So that the A plus ions are replaced, the electrolyte solutions, whatever those A plus ions are going to be replaced by the C plus ions present in the reagent solution. So this replacement of the ions with the other ions shows the conductance, whether increase or to a decrease level. So this is done mainly by the replacement of hydrogen ion with other cation. Okay, so this is the main principle involved in the conductometric titrations. So if you are seeing some important definitions and laws related to the conductometric titrations, first of all, the basic law that is related to the conductometry, that is Ohm's law. So as we have already studied about Ohm's law in our previous classes also, according to this law, the strength of the current, that is it is represented by the I, flowing through a conductor is directly proportional to the potential difference applied So that is nothing but here I is the current and E is the potential difference. Okay, so this potential difference is applied across the conductor and inversely proportional to the resistance of the conductor, that is R. We know that R indicates the resistance, whereas I is the strength of the current. Okay, so E is the potential difference here. So Ohm's law is stating that I is directly proportional to E as well as inversely proportional to the R. So if you know the resistance, you can calculate the current. Okay, so conductance, what is defined by the conductance, that is, it implies that the ease with which the current flows through the conductor, thus the conductance is reciprocal to the resistance. So 1 by R is nothing but the reciprocal of the conductance. Okay, so that is expressed in terms of the resistance only. Now the other definition, that is molecular conductance. So what is molecular conductance? This may be defined as the conductance of a solution containing 1 gram mole of the electrolyte when placed between two sufficiently large electrodes. So when electrodes are present, then two sufficiently large electrodes are there, they are 1 centimeter apart. Okay, so if they are 1 centimeter apart, then the electrolyte solution concentration is 1 gram mole, then it is called as the conductance presented by the solution is molecular conductance. So it is denoted by micron symbol and it is measured in mhos. Okay, so the other definition, that is specific resistance. So if you see specific resistance, it is represented by rho. It is not P, it is rho. Okay, here you can see. We can call it as rho. So R equal to rho into I by A. So it is the resistance offered by substance of 1 centimeter length and 1 square centimeter area. So specific resistance is nothing but R equal to rho by 1 by A. Okay, so where rho is the specific resistance or resistivity and L is the length, here they have represented this one as the length and A is the cross sectional area of the homogeneous material, right? So in this, if you see, the resistance, specific resistance is going to be defined here. So similarly, if you know the resistance, you can define the conductance. Okay, so what they have done, according to that, they have defined a specific conductivity and they have represented this one as a small kV. So it is a conductivity offered by a substance of 1 centimeter length and 1 square centimeter surface area. Okay, same resistance is inversely proportional to the conductance. So specific resistance is inversely proportional to the specific conductivity, but the unit of measurement here, it is a reverse. Ohm inversely proportional means it is mhos, centimeter inversely means centimeter inverse. Okay, so that is the difference here. Now coming to the equivalent conductivity. What is equivalent conductivity? It is represented by lambda V. So it is the conductivity of a solution containing equivalent weight of the solute. So equivalent weight, molecular weight are going to be different. So it is the conductivity of a solution containing equivalent weight of the solute between electrodes at 1 centimeter apart and 1 square centimeter surface area. Okay, so for this, unit of measurement is mhos into centimeter inverse. So now let us see what is the relation between this specific conductance and equivalent conductance, all these things. Okay, so let us have the different relations between them. So consider a rectangular metallic vessel with a opposite sides exactly 1 centimeter apart, but it is actually practically it is difficult, but let us assume that a rectangular metallic vessel with opposite sides exactly 1 centimeter apart. If 1 cc of the solution, like 1 ml of the solution, is now placed in this vessel, the area of the opposite spaces of the cube covered by the solution will be 1 square centimeter. Okay, so if 1 cc of the solution is placed in the vessel containing 1 gram equivalent of the electrolyte, let us assume that a metallic vessel is there, one rectangular metallic vessel. So in this, if you are containing 1 gram equivalent weight of the electrolyte, then the measured conductance will be equal to the equivalent conductance, because it is an ideal condition, that is 1 centimeter, 1 ml, okay, 1 square centimeter area. So all are the units. So unit of measurements is going to be taken as one value. So then what happens? The specific conductance is equivalent to the equivalent conductance. dilute this 1 cc of the solution. That means 1 ml of the solution can be diluted to 10 ml by adding 9 ml of the pure solvent. So here what we have written is that is 1 cc of the solution to 10 cc of the solution by adding 9 cc of the pure solvent. So the equivalent conductance, however, will be 10 times as the specific conductance. So that they have represented as lambda equal to K into 10. Okay. So if you are going to dilute that by 10 times. So if the solution containing 1 gram equivalent of the electrolyte which is dissolved in VmL. Okay. So VmL of the solution, 1 gram equivalent of the electrolyte in VmL of the solution, then what happens? Lambda equal to K into V. So 10 means it will come around 10. 1 means 1. Okay. So like that. Hence, equivalent conductance. How we are going to relate with the specific conductance? Specific conductance multiplied by the volume of the solution which is containing 1 gram equivalent of the electrolyte. Then only this is applicable. Right? Now, relation between molecular conductance and specific conductance. If you see the relation which exists between molecular conductance and specific conductance is quite similar to the relation between equivalent conductance as well as specific conductance. Say here also same, you can see this molecular conductance we are going to represent like this, lambda V equal to K into V. So specific conductance and volume of the solution which is containing 1 gram mole of the electrolyte. Right? So molecular conductance and equivalent conductance same as molarity and normality. If you are talking about normality, gram equivalent weight. If you are talking about molarity, molecular weight, gram molecular weight. Similarly, molecular conductance means 1 gram mole of the electrolyte is going to be taken, and equivalent conductance means 1 gram equivalent of the electrolyte is going to be taken. Okay, same concept. Now the important aspect in conductometry titration, that is cell constant. Okay, because 2 electrodes are present there. So the electrodes in the cell, actually speaking, they are not exactly 1 centimeter apart and may not have surface area of the 1 square centimeter. Okay, so the value of the observed conductivity is not equal to the specific conductivity, but sometimes it will be different. That means it is proportional to it. So it is important to calculate a factor for the conductivity cell known as cell constant, because always 1 centimeter length, 1 square centimeter area cannot be measured. Okay, so the cell constant when multiplied by the observed conductivity gives the value for specific conductivity. Here specific conductivity. So the cell constant, whatever it is there, we need to develop that. It is going to be multiplied by the observed conductivity value will give the specific conductivity. Okay, so that is mentioned as R equal to rho into 1 by A. Okay, so or L by A, not 1 by A. Okay, so R equal to rho into where X equal to here R equal to P into X, they have mentioned like this. So don't get confuse that whether it is P or rho. Okay, so just focus on the what it is actually. So here cell constant is going to be expressed in terms of 1 by observed conductivity or 1 by specific conductivity. Okay, so specific conductivity formula we are going to write as cell constant into observed conductivity. So like this. Okay, here 1 by observed conductivity, here one line is there. Okay, so divided by is there, cell constant equal to 1 by observed conductivity, 1 by divided by 1 by specific conductivity. So specific conductivity is going to be coming towards the upside, then specific conductivity is equal to cell constant into observed conductivity. So finally the formula comes like this. Okay, so don't get confused here, some line has been missed, that's why. Okay, so determination of the cell constant, how we are going to determine? The cell constant is determined by substituting the value of specific conductivity of n by 50. That means normality, 1/50th normality of the KCl solution at 25 degrees centigrade. So this value as determined by the 𝘂𝙬𝙎 was, who is the scientist, have determined. So that has to be calculated, and after all calculations he got that 0.002765 moles. Okay, so the value of conductivity is then observed with the given cell using n by 50 KCl solution. So the cell constant is then calculated by using the following relation. That is, what is that? Cell constant equal to 0.002765 divided by observed conductivity. Okay. So this is what they have developed. That means it is going to be corrected. Always cell constant is may not be the same value. That's why it varies from electrode to electrode. Okay, the manufacturer will provide the value also. Thereby you need to correct it with the observed conductivity value by multiplying with the cell constant. Okay, so afterwards we need to carry out the analysis. That means how we are going to measure the conductance. So it has already seen that the measurement of conductance is a measurement of resistance, right? Because it is a reversible reciprocal of the conductance. So the Wiedstern-Bridge method, here the bridge, the circuit, whatever they are going to use, that is Wiedstern-Bridge method. Therefore we use it for its measurement. Okay, here you can see the picture of the Wiedstern-Bridge method. So in this you can see earphones, jack keys, and source of alternating current. Okay, so everything is set in this Wiedstern-Bridge. Okay, here resistance is measured here, like here, and this A and C, it is going to be between D point is also there. So all these are incorporated in this Wiedstern-Bridge. So it is called a variable resistance. So box is also there. Okay, so this Wiedstern-Bridge method is going to be used for measurement of the conductance, and this bridge is going to be connected to the electrodes. Thereby we are going to put the electrolyte solution in the conductivity cell. Okay, so this whole the equipment is called as a conductivity cell. So from this we are going to see what is the current flowing inside that, and by the inversal of this resistance we will get the conductance. Okay, so the following are the different bridges used for the measurement of the conductance. So what is that? 𝘂𝙎𝙎𝙎 bridge, Wiedstern-Bridge also we have seen just now. So similarly one more, that is 𝘂𝙎𝙎𝙎 bridge. It consists of a meter bridge wire AB. Here you can see this is the AB wire with a fixed resistance on both ends. Okay, so R fixed resistance. To increase the length of the wire, it is connected to a resistance box. Okay, so this resistance box is connected here, and conductance cell C and the headphone D, and a small induction coil is also there. Okay, so here conductance cell is there and headphones D, small induction coil is also incorporated here. So all these are actually operated by the battery. So actually why this headphone? This headphone is used for the detection of the conductance difference. Okay, so this is one of the bridge method that has been developed by 𝘂𝙎𝙎𝙎. So Wiedstern-Bridge method and 𝘂𝙎𝙎𝙎 bridge, these two are going to be used for measurement of the conductance. Okay, so one more, that is direct reading conductance bridges. That means headphone replaced by 𝘂𝙎𝑒𝑖, which is an electronic device. Sometimes this is going to be also used, and recent equipments are going to be different rather than this. Okay, so most of the developments have been taken place while manufacturing this conductometry. Now how we are going to do the method of measurements, let us see. So the solution whose conductance is to be measured is taken in the conductivity cell. So the electrolyte solution, whatever it is there, it has to be taken in the conductivity cell. So it is known that the conductance varies with the temperature. We know that conductance ions, mobility of the ions is going to be according to the temperature. So it is therefore necessary to keep the temperature of the solution constant throughout the experiment. So whenever you are going to do, please maintain the constant temperature. Okay, so thereby this conductivity cell has to be kept in thermostat so that constant temperature is maintained. The cell is connected to a resistance box, that is R on one side, and to a long thin wire, that is AB, stretched along a scale on the other side, what we have seen in the previous slide. So now some known resistance R is taken out of the resistance box. Okay, so whenever the mobility is going to take place, the resistance is going to be built up. So an alternating current is passed through the solution with the help of an induction coil will be there. Okay, so the sliding contact D is moved on the wire AB so that that minimum or no sound is heard in the headphone. Okay, it is going to adjust in itself. Then no sound is going to be heard. So at this point what happens? The relationship holds good. That means resistance of the solution, it is going to balance itself. So resistance of the solution divided by complete resistance, which is coming from the box, is equivalent to the length BD divided by length AD. Okay, so AB wire is there, so we have connected to the D, so that means the length it is going to be adjusted, so the ratio is going to be proportional, right? So knowing R and AD values and BD values, the resistance of the solution can be calculated. So if you know the length, okay, AD and BD values and R value, then resistance of the solution can be calculated from this formula. Since conductivity of the solution, we know that 1 by resistance of the solution, therefore knowing resistance of the solution, the conductivity of the solution can be calculated. Okay, so that is the principle involved in this conductometry. Now let us move to the instrumentation part. So the instrument used for measurement of conductance are known as conductometers. Okay, so conductometers are which are going to measure the conductance of an electrolyte solution. So it consists of what? Current source, so which will give you the alternating current, and second one, conductivity cells are present, which contains different types A, B, C. Okay, and electrodes will be there, a cathode and anode. Okay, so current source, actually what are the current sources means different types of the current has to be cannot be taken, right? So the alternating current has to be produced. So what is the source of the current means mechanically high frequency AC generator, and which has been developed with this Washburn, and the second one, Taylor and Acri, who has suggested use of oscillator for producing the AC current, and third one, vacuum tube oscillator, okay, which has been suggested by Hall and Adams. Okay, so these three types of the sources are there to generate the current. So when electrical potential is applied across the electrodes, two electrodes are there. So when an electrical potential is applied on two electrodes, the two process occurs. So what are those? Ions accumulate near the electrodes because it is going to move towards the opposite charge. Then transfer of the charge through the interface is going to take place. Okay, so first one, what happens? Ions accumulate near the electrodes. Second one, transfer of the charge through the interface. So here we need to focus on that. DC current is not employed in conductance measurement because electrodes become polarized, leading to high cell resistance. That's why AC current only it is used, alternate current. Okay, so these two processes are going to take place whenever we are going to apply some potential on the electrodes. So these are the different types of the conductivity cells. So these are made up of pyrex or quartz. Here they have mentioned that pyrex are quartz and are fitted with two platinum electrodes. Okay, so all the conductivity cells are made up of either pyrex or quartz. So two platinum electrodes will be there. So they are placed in vessel containing water to maintain constant temperature always, because water is also give the conductance, right? So here type A, B, C. So first one is the A, B and C. These three are the different types of the conductivity cells. Okay, circular path will be there, and here because only the manufacturing method is only the different. Okay, so different shapes, these type A, B, C conductivity cells are available. Okay, so coming to the electrodes, platinum sheets each of 1 square centimeter are fixed at the distance of 1 centimeter. The surface is coated with platinum black. So all the electrodes surface is coated with platinum black to avoid the polarization effect and increase the effective surface area. Okay, so platinization of the electrodes is done by coating solution of 3% chlorplatinic acid. So how the platinum black is going to be there? That is, they are going to coat the electrodes with 3% chlorplatinic acid and lead acetate on it to get the uniform coating. This is the material they are going to use it. So electrodes usage depends on the conductivity and the concentration too. So what is that? Conductivity and concentration. So if concentration is low, then electrodes should be largely and closely packed. They are not going to move. Okay, so determination, how we are going to determine the conductance by using different types of the conductometric titrations. So determination of the endpoint of a titration with the help of conductivity measurements is termed as conductometric titrations. So we are going to determine the endpoint of the titration. How we are going to do in a conductometric titration? The titrant is added. Similarly, what we are the basic concept in titrometric analysis. Okay. So here also in conductivity cell the titrant is added. So the values of the conductivity are then plotted against the volumes of the titrant in cc, that means ml, right? Since the measured conductivity is a linear function of the concentration of the ions present, right? So if the ions are present means the conductivity will be more. So two lines will be obtained which will intersect each other at a point which is known as the end point or equivalence point. Okay. So at one point because concentration increases, then conductance also increases. So at one point, if the concentration, all the ions are going to be captured by the titrant, then you are going to see one endpoint. That is called as equivalence point. So exactly in conductometry, we are going to get the equivalence point. Okay, that is itself, it is here call it as endpoint also. So this is whenever we are going to use the conductivity cell. Okay, so if you see the in this picture, conductivity meter, it is conducted here. So what we have seen in the first slide, and this is the conductivity cell, the total flask like this. This is the conductivity cell, and here magnetic stirrer will be there because while adding the from the burette we are going to add the titrant. So thereby the solution should be in the mobility state. Okay, mobile state law, it has to be there. Then so while stirring only you need to measure the conductivity. Okay, so all this. So and this is the electrode, black color one, platinum electrode. Okay. Now let us see what are the types of the conductometric titrations. Similarly, in titrometric analysis, how we are going to perform different types of the titrations. In conductometry also, acid-base titrations we can perform, replacement titrations, redox titrations, and complexometry as well as precipitation titrations also we can perform. So coming to this acid-base or neutral titrations, strong acid, strong acid, weak base, weak acid, strong base, as well as weak acid and weak base. So all these types of the titrations we can perform by using the conductometry. Okay, these are some of the examples of all the strong acids, strong bases, and different types of the weak acids and weak bases. So if you see one example, strong acid and strong base fall in conductance due to the replacement of the high conductivity of the hydrogen ions, okay, by poor conductivity of the sodium ions. Here one example, that is HCl versus NaOH if you are taking, that is strong acid versus strong base, right? So replacement of the high conductivity hydrogen ions, okay, because in H plus Cl minus you are going to see H plus ions, so those ions are going to be replaced by the poor conductivity of the sodium ions. Okay, so thereby you are going to see initially the conductance will be more because of the H plus ions, and this rise in conductance due to increase in the hydroxyl ions here. Okay, so if you see the volume of the NaOH, if you are going to add here, and conductance initially it is going to be very high due to H plus ions. So by adding sodium hydroxide, it is going to decrease. Okay, so whenever all the neutralization is going to take place, you are going to see the depression here. So afterwards it again tends to increase because of the OH minus ions, because H plus ions are conductance is more than OH minus ions. That's why initially you are going to get the conductance by H plus ions. So after the end point all the H plus ions are going to be consumed, then the conductance is due to by the OH minus ions. Okay, so this why this again increase in the conductance is going to be observed here. So the intersection of these 2 points is going to give you the volume of the base. So that is actually it is considered as the end point. Okay, now let us see the another type of titration, weak acid and strong base. So initial decrease in conductance is due to the increase due to the NaOH. We know that weak acid and strong base, okay, means NaOH. So due to the hydroxyl ions, some conductance will be there. So while adding in weak acid, you are going to see CH3COOH if you see. So CH3COO minus acetate ions are going to be there. So due to that you are going to see some less conductance. So whenever strong base sodium hydroxide is added, then the conductance is going to be increased here. So afterwards again some neutralization is going to take place. So that point is going to be correlated as conductance. Okay. So here exactly the points have been represented, but generally the intersection point is going to be taken. Okay. So the curves will be like this. So then the intersection point is going to be taken as the end point. So one more example, weak acid, weak base, that is acetic acid and ammonia. So in this ammonium hydroxide they have taken. So initial increase in conductance is due to the excess of the acetic acid. Okay. So rise in the conductance is going to take place, and suppression is suppression of this ammonia NH4OH is by the acetate. Okay, acetic acid is going to take place. So volume of the NH4OH is going to be increased. Thereby the conductance is also going to be increased. So after the end point, the suppression is going to take place, and you are going to see a plateau. Okay, straight line is going to observed. That is the actual intersection point. We are going to consider this one as the end point. So redox titrations. If you see the application of the conductometry principle in redox titrations, we know that both oxidation and reduction both are going to take place in this. So if you are seeing some chromate ions with iron, then how this reaction is going to take place. But all the compounds which are going to take place, both oxidation as well as reduction, we can perform the conductometry very well. So here if you see, the end point is here. Okay, so the conductance initially it is more, thereby it is getting slowly down. So afterwards it constantly will be there. Okay, so the intersection of this point is going to be taken, and complexometric titration. So if you are going to see some different types of EDTA titrations also there. So if you are seeing the curve for the complexometric titration, okay, so initially the this volume of the EDTA, whenever we are going to add this, then you can see here the conductance is going to be around somewhat different, but here they have mentioned in decimal points also. Okay, so initially it is somewhat increased, afterwards the equivalence endpoint will be there. Okay, so whenever this EDTA is going to be forming the complex, then again the plateau is going to be observed. Okay, now coming to the precipitation titrations, if you see the conductivity is going to be taken on y-axis and precipitant added, whatever the silver nitrate solution is there, so it is going to be on the volume on x-axis. So you can see the titrations are going to be carried out where the precipitation is going to takes place, and due to that precipitate the conductance is going to be changed. Okay, so initially it is going to be like this, and afterwards it will increase like this. So here this is the end point. Okay, so this is how we are going to determine different types of the analytes by conductometric titrations. Okay, so coming to the advantages of the conductometric titrations, which does not require the indicators, visible indicators, what we have used in the acid base titrations. Okay, non-aqueous titrations, all these color change indicators are not required here, because here we are going to measure the conductance. Okay, so suitable for the color solutions also we can do, and since endpoint is determined graphically, by means accurate results are obtained with the minimum error. So this conductometric titrations can also be used for the analysis of the turbid suspensions, weak acids, weak bases, and mixture of the weak acid and strong acids also. Okay, so weak and strong acids are also can be in the mixture form, we can identify. So temperature is maintained constant. You need to maintain the thermostat. You have to keep the conductivity cell in the thermostat, means the constant temperature can be maintained, and this method can be used with much dilute solutions also, very highly diluted solutions also we can estimate amount of the analytes present in the electrolyte solutions. Okay, so apart from the advantages, we have some disadvantages also. What are those means? So increased levels of the salt in the solutions mask the conductivity changes. In such cases it does not give the accurate results. Okay, some types of the salts will be there which at the high levels are going to mask the change in the conductivity. That means endpoint cannot be accurately determined. So in some cases applications of the conductometric titration to redox system is limited. So what we have seen, both oxidation and reduction is going to take place. Sometimes it is limited application because high concentration of the hydronium ions, okay, H3O plus ions are going to be there, which leads to mask the change in the conductance. Okay, so H plus ions, OH minus ions, the conductance will be there, but H3O plus ions also are going to give you the some conductance, which may give you some erroneous results. Okay, so finally the application part of the conductometry, that is degree of dissociation of the weaker electrolytes. We know that weak acids and weak bases cannot be accurately determined by some type of the titrations. So in such cases, degree of dissociation of the weaker electrolytes is going to be major problem. So the degree of dissociation of these weaker electrolytes is given by the formula A equal to lambda V divided by lambda alpha. So where is lambda V means equivalent conductance at the given dilution, and lambda alpha means equivalent conductance at the infinite dilution, and A can be found experimentally. Okay, so this is if you know these two, you can determine this. So hence a degree of ionization of the weak electrolytes can be calculated. So other applications if you see, so we can also determine sulfur dioxide in the air pollution studies and soap in the oil. Okay, so and determination of the accelerators in the rubber and total soap in the latex, these are also can be determined, and specific conductance of water, we know that 𝘂𝙬𝙬𝙬. Okay, and check water solubility in rivers and lakes. So those samples can be taken and they will check for the water solubility also, and alkalinity of the fresh water, that means how basic it is, that one also, and salinity of the seawater also can be determined by this conductometry, and deuterium ion concentration in water deuterium mixture. We know that water H2O deuterium is going to be replaced, that means D2O. So if the mixture is there, then the concentration of the water ions can be determined here, and deuterium ions also can be determined. Thereby subtraction we can find it out. Okay, so food microbiology for tracing the microorganisms, and finally tracing the antibiotics. So all these applications can be performed by conductometry titrations. So another some type of the applications, that is estimation of the ash content in sugar juices. Okay, so in juices where most of the glucose is going to be there, so in that ash content is there or not, we are going to can determine by this conductometry, and purity of the distilled and deionized water can be determined, as we have already discussed in the previous slides also. Ionic product of the water can be determined, so thereby distilled water and deionized water purity can be also determined, and solubility of the sparingly soluble salts like silver chloride. Okay, so it is a sparingly soluble salt, so the solubility of this also can be detected, and estimation of the vanillin in the vanilla flavor, this can also be determined by conductometry, and determination of the atmospheric sulfur dioxide as well as basicity of the organic acids and degree of the hydrolysis, like what we have seen in our previous slide. So all these applications can be performed and we can use by conductometry titrations. Okay, so hope all this information is going to be useful for you, and how the conductometry can be performed, how the concept is the instrument is very small, but if you know the type of ions we are going to be involved in the titration, then you can very easily perform the conductometry. Okay, so finally we conclude that by using conductometric titrations, we can estimate the endpoint by plotting two straight lines using the usual graphical method, right? Because intersection is going to be taken as the endpoint. So endpoint determined by measuring the conductivity only. So this theory is used for the colloids that have ionizable functional groups like latex. So this titration process can be used for either turbid or colored solutions also, where you can endpoint determination is going to be very normal by the indicators. There somehow difficult is going to be means difficulties are going to be there. So all those difficulties can be overcome by this conductometric titrations. Okay, so hope you understand well. Thank you, students.